And first of all, my name is Siddhartha Sarcher. I will be facilitating this webinar today, and I'm a research manager here at IFE. In the invitation that you got when you signed up, it was highlighted that the webinar is going to be recorded. So I just want to mention that again, that the recording has now started and it will be made available afterwards. It's only the speaker presentations that will be included in the final recording. So none of the discussions or the questions and answers will be part of that. And it's going to be made available afterward in the sort of webinar's website. So before we continue, I would also like all of you to mute your microphone and turn off your cameras during the presentations. And after the presentations, it will be a small session where you can ask direct questions to the speakers. And at the end, we will have a separate session for questions and answers. Here is the program for the webinar. So the first part will basically be some introductory part from the Institute for Energy Technology, where we'll go a little bit about IFE, the Halden Technology and Organization Project, introduction to SMRs, and then the potential use cases of this in Norway. After that, we will sum up whether there are any questions related to these 4 presentations before a break. And after that, we will continue with the external speakers on nuclear energy risk, future EU environmental requirements, consequences for the Norwegian shipping industry, and then on the nuclear situation in Europe, what opportunities there are and barriers, and also nuclear power in Norway. Each of them will be given the option, or you will be given the option to ask questions to each of them, and also at the end we will have an audience questionnaire. For this webinar, I would like to prioritize questions that are raised. So you may raise your hand after each presentation, but you may also add your questions in the chat, and we will try to follow up on those the best we can. With that, I would like to introduce our first speaker, which is Thomas Nolander. He is the Vice President of IFE Research and Development, and specifically for digital systems.
Thank you, Siddhartha. I would give you a very short background about IFE. IFE is a research institute. It's a research foundation. It's a non-profit foundation. That means that we are not owned by the government. We're not a university. We don't have any shareholders. We own ourselves. We started our existence after the Second World War. And here on the picture on the left, you see our founding father, Gunnar Anders, together with Albert Einstein. He was over in US at this time and got to know Albert Einstein and his work, but also his colleagues. And this was a time when US was relatively open when it comes to nuclear technology. And that and a good relationship to US allowed Norway to be the 6th nation in the world when it comes to nuclear power. So even though we today don't use nuclear to produce power, we have had 4 nuclear reactors in Norway that we have built from scratch. And it's in IFE, the Institute for Energy Technology, where we have built these reactors. And these reactors were up until end of 1970s meant to get the knowledge for us to maybe have nuclear power in Norway. But then due to political decisions, 1979, it had a more focus on reactors for research. But over this time, IFE was built, and it was built in one way to help Norwegian industry after the Second World War. And during this time, we have started with nuclear, but we also walked into hydrogen, offshore, wind, subsea, solar, battery, etc., and become an energy research institute. At IFE, our main office is in Kjeller, just outside Oslo, on the way to the airport. And the other location at IFE is on the border to Sweden in Halden. And IFE is different in many aspects from other research institutes, is that we have 3 very distinct organizations under one and the same roof. So we have research and development, and that's part of us here. And then we have nuclear operation, and that is a part with a couple of hundred people that maintain and run the reactors. And then we have in blue here organization which produce radiopharmacy for prostate cancer that are delivered around the world. But the one that present the seminar and set it up here, it's under research and development. And here we have 2 divisions, energy and miljöteknologi and digital system down here in Halden. And I will just focus a little bit, 2 more slides about that before I leave over to Andreas. So we're called digital system, but what we focus us in how we can use digital technology to do more with less effort and get it done quicker, safer, and cheaper. And this is something that we have done for the international nuclear community for a long, long time. But the knowledge that we have gained is very applicable for the Norwegian process industry, etc. So down here in Halden, where we have one of our reactors in the mountain here, we have 3 different research areas: human and organizational factor, risk, security and physical science, and artificial intelligence, and virtual and augmented reality. These 3 different sectors or research areas consist of 7 different departments. We have 11 labs, 2 research centers, and are about 100 employees. But on the right-hand side, we have something very interesting when it comes to you interested in small modular reactor. We have the Halden Reactor Project. IFE have run one, if not the largest international research project and the longest running. So we are running a project that we started in 1958. And in this project or this consortium, you have over 100 organizations from 20 different countries that are every year paying us money to do applied research for them in nuclear safety. And of course, that means that this have gone on for decades, and this is our biggest project at IFE. And it's the absolutely biggest part of what we're doing down here in Halden. But this project, since 1958, have formed and fed the creation of these different departments here. But if you look on the left-hand side, this department, you see that a lot of the names of the department, you can very quickly see that they are very relevant for other areas of society, if it's industry or smart city or energy in general or in transportation. And very often, a lot of research institutes say that they are very good or world leading in these areas to the left. And of course, we say that too. But during this Halden reactor project, every 3rd year, all the countries and organizations can pull out. So there are 3-year projects that continue if everyone agree, and they have continued since 1958. So that means that US have decided to send a lot of money to Halden for us to do research on nuclear safety for them. And in England, they have not sent it to Oxford, Stanford, and Edinburgh, they're sending it to us. The same in Sweden, they don't send it to KTH Uppsala, they send it to us. And the same in South Korea, in Japan, in France, etc., etc. So in the area on the left-hand side, when it comes to nuclear safety, we are world leading when it comes to research there. And then with that, I would like to move over to our next presenter that actually have the responsibility for the Halden reactor project, or the HTO project. Then, Andreas, I would close my presentation and then you can share the screen.
Good. So I'll just continue from that introduction. My name is Andreas By. I'm a chief scientist at IFE, and I'm a program manager for the Halden project, the OECD NEA Halden Human Technology Organization project. So I'll talk a little bit about that and how that is relevant for SMRs. A little bit about the history. Thomas mentioned it, but this is based on the Halden reactor that was built in 1958. There has been a project going on since then, but the Halden reactor was closed down in 2018. So we were wondering whether it was possible to continue a Halden project after that time. We started also very early with process control at the reactor in 1967 already. There was a chapter on doing research on process supervision and control at the reactor. We had a first system called OPCOM in 1972, which was computerized control of the Halden reactor. We can see a picture of that up here with Tonberg TVs and a graphical system made here at IFE and a homemade keyboard and everything. So that was one of the first digital control systems of nuclear reactors in the world, actually, in 1972. We wanted to continue research on this and found out that we needed the simulator laboratories in order to be able to do that in a good way, since we were also interested in safety and how to handle accidents on a nuclear facility, and for that we needed a simulator. So the first version was built in 1983, and we've had 4 versions and buildings since that time. I'll come back to that a little bit later. So what is this Halden project, or Halden reactor project? That started in 1958 as 3 yearly projects, and there was a fuels and materials program in green here, and there was a so-called MTO program, Man Technology Organization program. In the last years before 2020, the fuels and materials program had approximately 60% of the turnover in this project, and the MTO part had approximately 40%. So we were, of course, very excited or a little bit nervous when the reactor closed down. A very big infrastructure in here. Whether we would be able to continue this program after the reactor was shut down. I'm not sure how many of you who knows about have heard about the Halden reactor, and I guess if there are any one of you having heard about the Halden project, I'm pretty sure maybe some of you don't know that there is still a Halden project going on. This is about what I'm going to talk about now. We renamed the MTO part of this program to HTO, Human Technology Organization. We started 1st of January last year with this project. And it is built on the same type of structures than as the old project, but it's moving on with the issues on control rooms, with safety, with human technology and organization. So what is this? This is an international collaborative research project for safe and reliable operation of nuclear power plants. So it's a nuclear power safety program. It's affiliated to the OECD Nuclear Energy Agency in Paris, and IFE is the operating agent. IFE here in Halden, all the activities are going on here, and it's a 3-yearly joint research program. It is funded not by the NEA but by the membership, country membership. So the agreement is now signed by 20 parties in 12 countries, including Norway. And there are, in addition to that, there are now 39 organizations who are pre-approved third parties, and that's typically regulatories, utilities, or power plants, and vendors, R&D centers, and even then, for example, in Norway, we have Equinor or oil companies, and NTNU, and NND is with us, and the Høgskolen i Østfold as well. The budget for the 3-year period is approximately 150 million Norwegian kroner, which is a little bit less than the 40% we had of the old Halden project, but it's we managed to establish it, and currently it's actually growing. There's a growing interest in joining this. The members of this project in Norway, IFE is a formal member, but the funding is coming from the government. Canada is joining for the first time. They have a good constellation of the regulatory safety commission, the authorities, the Canadian nuclear laboratories, and the county owners group, representing the utilities and the plants. While it's the same kind of constellation we see in the USA, where Department of Energy is now the biggest party. The US Nuclear Regulatory Commission have been maybe the most important member in all the years for the human factors and the MTO, HTO research. They are a world-leading party in the nuclear power and nuclear industry, and most of their guidelines is taken as kind of ad hoc or as standards used by all the countries in the nuclear world, actually. So many of these countries are now also interested in SMRs. Small modular reactors is really hot in the nuclear world this day. We see Canada have a lot of efforts in it. The US has a lot of discussions, and most of the countries, and UK as well, are discussing that. And most of the countries are interested because they see it is coming as a safer option and a new option of doing a better job also on the safety and efficiency of the nuclear industry. Okay, I'll talk a little bit about the drivers for establishing this new Halden Human Technology Organization project in 2021. And it's quite interesting to see that people's the importance of the human aspects of nuclear safety is really getting on everybody's mind. The Nuclear Energy Agency, they established this division of radiological protection and human aspects of nuclear safety in 2014. Before that, they had nuclear safety divisions, but now they had a separate entity of human aspects of nuclear safety. And that was a key point for us, I think, when we wanted to establish this new one. I'd also like to say that for the nuclear industry, the importance of safety and safety research is really important. The whole industry has an obligation to do science-based developments. And so I would say that when it comes to control rooms, surveillance, digital I&C, and now we also see, for example, cybersecurity, and especially human factors, we see that the nuclear industry has really been willing to put money into research in this on these aspects. Maybe more than other industries, I would say. Of course, some of the important drivers here were the accidents that has happened. For example, at 3 Mile Island in 1979. Short time after that, we established the first simulator laboratory here, and so that has been instrumental. Also, we have learned a lot from the Chernobyl and the Fukushima accidents, of course. And now we have very good contact to utilities as well. I'll say a little bit, talk a little bit about our infrastructures. We are, as Thomas said, we are an applied research institute. We are very empirically based. So we have simulator laboratories with the full-scale simulators, for example. We have a virtual reality center, and so on. This is our Halden Human Machine Laboratory, HumLab, has been in operation since 1983. And here we do research and experiments with licensed crews, with the real operators from power plants, typically from Sweden or from the US. A picture of these guys here, it's taken from the gallery where we are surveying these experiments. This is a crew from a US nuclear power plant who comes here for 1 week. They have a training 1 day, and then they're running 4 days of scenarios to support our research. And our research is typically about how to make best possible interfaces, best possible overview displays, for example, to get a better view of the plant. It is about the scenarios, what type of scenarios are really creating problems for the operators. And to do these things, we have people employed here who has been operators at power plants. We have engineers, of course, and computer scientists. But last but not least, we have maybe the biggest group of psychologists working on these matters in the world, actually, where we have 15 or 20 psychologists here who are working on setting up experiments and testing these safety issues with operators and crews in realistic scenarios, which is different from universities who have much more like students as a subject base, but we can do more realistic things here. How much time do you have, Susanne?
You have some more time.
Okay, 5 minutes, good. This summer we installed a small modular reactor simulator in our HAM lab. This was installed in August. It was the first SMR simulator to be used for research purposes in the world. So we are on the leading edge of this. This is a light water technology simulator, currently with 6 units, and we can expand it up to 12. And the point here is that here we want to do research on multi-unit surveillance, teamwork, for example. How many operators do you need to survey 6 units, for example? There's a lot of research questions coming up, and the surveillance of 6 similar units is different from the surveillance of 1 big unit earlier. So that's a lot of interesting research questions coming up, actually, that regulators worldwide are asking us about results on this. We have a virtual reality center as well, been working a lot of that especially in decommissioning. We have a decommissioning cluster here in Halden now, and working together with the Norwegian Nuclear Decommissioning and others, and Smart Innovation Norway, for example, working together with them on a cluster and on a lot of things on the robotics. And here we are using VR, augmented reality and extended reality. We have a future lab where we are more exploring issues earlier in the design phase. And I'll mention also that we are working on cybersecurity as well. And in that's a typical case that shows that we work empirically and we want to have applied research. So here we have established a security operations center. And our speciality here is actually to look at how are people surveying this and how can people in such a center collaborate with operators in control rooms in order to together handle attacks on serious infrastructure, for example, power plants or others. We have what we call a HADRON, hazard-aware digitalization and robotics in nuclear and other domains. And here we are utilizing robotics for, especially in decommissioning, I would say. We have a human automation lab. It's a nice picture of a CSAR type there. And we are working also on physical measures, eye tracking, for example, EEG things we have done for quite some time. I'd also mention that we have what we call a remote lab. You will meet Rob McDonald later. It's a picture of him. He's here collecting data at the plant, US training simulator at a nuclear power plant in the US. So these are the topics we are studying: human performance, digital I&C, safety assurance, control room design and evaluation, human automation collaboration, which is maybe the main thing that is related to SMRs now. If you look at it in that way, it's also very related to cars and our autopilots in the cars now and how we should collaborate with them. We have maintenance and operations. We have a digital transformation of decommissioning and also cybersecurity. So I would say many of these things are relevant and necessary to study if you want to look into SMRs. But I'll mention one particular thing is human automation collaboration, where we're looking at the human performance in SMRs, and especially about multi-unit operation. How can you, for example, how can an operator detect parallel failures in several units at the same time? How can you separate units from each other in different operational positions, and so on? Operator performance in highly automated plants is also very important, and it's also very, very relevant for other areas. So that's some examples. I think I'll stop there, Siddhartha, with this picture of our SMR simulator. And the message from here is that we are going to do empirical research in a SMR simulator in Halden in the coming years in this project. Okay.
Thank you very much, Andreas. Then we will move on to our next presenter. Sorry about that. I think we have it here now, which is, as you mentioned, Robert McDonald. He's a principal engineer from IFE, been that since 2014, has his background in nuclear plant operations and started his nuclear career in the US Navy, actually. Had 18 years in operations department at a commercial nuclear plant in Texas. Had 4 years in Ringhals in Sweden, in the control room there as a shift engineer, and has now sort of come to IFE and is one of the members in this SMR crew. The screen is yours, Robert.
Thank you, Siddhartha. It's my pleasure to be here today, and I thank all of you for joining us. I'm going to start off the discussion today talking specifically about the small modular reactors. So I'm going to start the process where we're going to look at technology. So today I'm going to continue right on through after I did the technology discussion. Claire Blackett is another one of our members, but she was taken ill this week. So I'm going to continue with her presentation afterwards at the end of this one. So I'll start with a little technology overview, and then we'll roll right into the other portion of her presentation. So I'd like to start off with the initial discussion is what is an SMR? What is a small modular reactor? And based on the NEA definition of small modular reactor, it's any reactor that is from 10 megawatts to 300 megawatts electric. Anything under 10 megawatts electric is considered a microreactor. And we'll be talking a little bit about microreactors as well today. The big difference with and why we say modular reactor is because with the SMRs, they're integrated and they're modular such that 90% of the construction of the reactor is done within a factory, and then that whole total component is shipped out to the site. And there's that makes it where it gets its competitiveness, because now you're not having to design and build everything on site or ship elements to the site. You know, you just basically do everything within a factory, a single factory, and then ship it out the site. There's still work done on the site as far as site planning and all the concrete pours and everything has to be done there. And then as of today, there are 70 different small modular reactor designs worldwide. Some of those are developing a little faster than others. And we'll be talking a little bit about that as well. So let's do a quick comparison of, because everybody, most people have this picture and idea of what a nuclear reactor and nuclear site looks like, based on the designs that were created back in the 60s and then built in the 70s and 80s. So these conventional, and I'll call them conventional designs as compared to a small modular reactor. So the conventional designs are between 700 and 1,400 megawatts electric, as compared to what we talked about, the SMR being between 10 and 300 megawatts electric. So about, anywhere from half to a third the size as far as output's concerned. And then we'll see how that works as we go. We talked about the modular design. Most of it's built in the factory. The last 10% is assembled on site, where with the conventional designs today, you have 70–80% of the construction on site. They are doing more modular construction today and shipping in some components, but the majority of it is constructed on site. Let's look at footprint. Site footprint for 195 megawatt electric plant is about 7 hectares or 17 acres. That same for a conventional design of 1,000 megawatts, you're looking at 259 hectares or 640 acres. So it's significantly still much bigger footprint. Potential uses: electrical generation, hydrogen production, district heating, desalination. Those are some of the things that you can use the SMRs for. The conventional designs are basically base load electrical generation. They are starting to do some support of hydrogen production, but that's very limited in the early phases. Safety systems for the SMRs are passive, and then we also use some inherent negative feedback reactivity as well for some of the designs, some of the Generation 4 designs. Most safety systems associated with the conventional designs are going to be active systems requiring electrical power. And so now some of the newer models, the AP1000, for example, they use more passive designs. So that's a step forward for those designs. But the newer SMRs are all passive systems. Scalability. Normally with the conventional designs, you get 1 or 2 units per site. So as I said, there's normally 1 to 2 sites. You can have some sites that have three units on the site. Whereas the SMR, the scalability, you can start with 1 to 4 units. NuScale is an example of this. Their design is basically a 12-unit plant, but you can start with as small as 4 and then expand those out based on the needs for capacity and what you have needs for electrical production in that area. So these are capable to expand, and so you don't have to put 1,000 megawatts in one place and then try to distribute that out. You can build that up, or you can move it to different areas. And then the larger designs, they're essentially designed for base load. They can do some load following, but it's not the most economical and best design for those larger plants, where these smaller SMRs can come offline or follow much easier because you're not trying to move such a large nuclear plant. So let's look at some of the safer designs with less waste. Let's look at this and here's a good example of an integrated system. So with this particular design here, we have the pressurizer within the reactor vessel, the cores within the reactor vessel, and then even steam generators can be created within this same thing. So you've taken essentially 3 major components: the core, steam generators, and pressurizer, and basically place them within one single reactor vessel. So this allows you a much cleaner system. Everything can be built within the factory instead of having to ship out these 3 major components to the site. You basically build everything in one area and then ship it out to the site. They rely on passive systems, natural cooling, so natural circulation to cool the plant, and then even some have basically set within a water tank such that it's flooded or able to be flooded in the event of an accident or the necessary to do so. So everything works on natural flow of natural gravity and natural circulation to cool the plant down. So no operator actions are required, and it helps reduce the risk of human error. Also, because we use a much smaller footprint and a much smaller, less material, in the long run, we'll have less radioactive waste to deal with. These plants are also designed to work much longer without refueling as often. Some of the more Generation 4 designs either have no refueling requirement or can go up to 7, 8 years, 10 years. So that also helps us reduce the waste at the end as well. And then just the size of everything helps also minimize that waste. So currently there are about 70 SMRs in development. Some of the SMR types are, you have the standard water cool reactor, light water, heavy water, pressurized water, and boiling water reactors. There's some high temperature gas cooled, including the pebble bed reactor. You have fast neutron type designs, which are both liquid metal fast reactor and gas modular fast reactor, and then molten salt, which are also fast neutron reactors, both chloride salt and fluoride salt cooled reactors. And you can see on the right-hand side of the screen, these are some of the manufacturers currently developing SMRs, both all over the world, essentially. So now I want to look at some of the current near-term manufacturers taking place today and where they're expected to start their production. So we'll start off with Westinghouse. It's an eVinci, their eVinci reactor. This is a micro reactor. So it's 5 megawatts electric output plus an additional 8 megawatts thermal residual heat that can be used for district heating or desalination. So they use a heat pipe technology. It's all contained within a single unit container, and then so they use this heat that comes from this reactor to spin a turbine to get your electrical output, and then that residual heat is also usable for different things. They're going to have their nuclear demonstrator up and running by 2025, and then they expect to have their production started by 2027 for commercial production. Seaborg is a Danish company that's using chloride molten salt reactor. They're using the molten salt technology. So their concept is a floating barge system that will have from one to 4 reactors. They're 200 megawatt electric reactors. So essentially, you can see in the picture down here that it'll be a floating barge. So this would be something that could be floated into a port, connected up to the grid, or for district heating, different possibilities. And as I said, it's expandable from 200 megawatts up to 800 megawatts. They're doing a demonstrator currently in Denmark. Oh, sorry about that. There we go. They're doing a demonstrator in Denmark right now to demonstrate the molten salt technology. The next one we'll talk about is GE Hitachi, the BWRX, and the X stands for number 10. This is their 10th design from GE. Currently, it is a boiling water reactor. It's a 300 megawatt design. So it's based on their latest design, passive design BWR plant, but scaled down to 300 megawatts. They currently are working with Ontario Power Generation in Canada at the Darlington site, just outside of Toronto. And they have actually just announced that they receive additional funding and approval to start site work and look at and some of the long lead items. So they're taking the next step. They're expected to have the first unit up and running by 2028. So they're taking the next step there as well. NuScale is one that's been in the news quite a bit. They were one of the first ones they are the first one to get U.S. nuclear regulatory approval for their design. They also have a commitment from a electric company in Nevada, in Utah, and they will build their first plant at the Idaho Laboratories testing site in Idaho Falls. So they move forward with that. They're in the process right now of doing their site verification and testing to verify that the site's prepared to accept the units. So they've done a 6-unit plan there, expected to be up and running by 2029, the first unit, and then the subsequent units by 2030. And then finally, the Swedish company, Swedish Advanced Lead Reactor. This is a cold lead sealer reactor is the name of the reactor. It's a molten lead technology. Its design basically is that it will be a 25-year life cycle, no refueling required. It'll produce 55 megawatts electric output. And one of the things that this is basically focused on is clean steel. So they will put it, or green steel. So they'll put it next to a steel production plant, and basically provide the electric output and some heat for the development of steel. So that's some of the technology and that's currently available and currently coming around. So that'll end that portion of this presentation. And then I'll move on to the next portion of the presentation. This was developed by, as I said, my colleague Claire Blackett, and then I'll do the presentation today. And we'll look at some of the benefits of smaller modular reactors. So this kind of goes right into from we looked at technology. Now we'll look at some of the benefits. So we know that we're looking to support a green shift, and renewables is one way to do that. But we also have to be realistic and think about how do we support that other half of that when renewables can't meet those demands. And as we move forward in the future, we need to think about what's the other process of, working between those two, both renewables and the other way to produce it, other means of producing electricity. So Europe is looking to power the nuclear power as a fuel to support the green shift. Here's a really good graph of how things work with a wind farm. You have varying outputs under the day, and this is from 4 o'clock in the morning till 4 o'clock in the evening. 4 o'clock in the end of the day. You know what I'm trying to get at. And so you can see that there's going to be some changes in the output. So you're going to need something that can support that as well. And so SMRs can easily do that as the wind picks up and more electricity is generated from the wind turbines. Then you can reduce the power from the SMR, and then that SMR can then pick up the power as the wind dies down and it changes. And if there is no wind, then you can just run your SMR as needed. So it's nuclear is definitely there and available, and especially with SMRs to support the green shift and then support those renewables as they come and go under the time period of the day. So there are cases for load following, and it works very well. A nice display here about the size, and when we talk about a 225 megawatt electric SMR, we look at about 15 acres of land as compared to the solar, which the same size is going to take up about 2,400 acres of land, and then your wind farm is going to take up about 6,000 acres of land. And these are it's just the numbers. So you can get a lot more power in a little bit of space, especially with the SMRs now. Then we talk about here the SMR design allows for much more flexible deployment. Because it has a significantly smaller footprint than the conventionals that we talked about, which were over 640 acres. Now you're down to somewhere between 7 and we'll say 20 acres for this development of this site. So it makes it much easier to be able to locate these in the areas that need electricity. And then if you get into smaller or into micro reactors, you're even talking even a less footprint. You're talking for a 10 megawatt microreactor, you're probably talking about the size of a standard warehouse. So for footprint wise, so it allows us, these SMRs allow us to be closer to the areas that we need that electricity. So then you don't have to build an extensive infrastructure to get the electricity from one to the other. Plus, it supports those things like district heating and other forms of heat requirement, desalination, and those things. So the recent uptake of the exploration of how microreactors and SMRs should be used as a sustainable alternative to energy. So if you're trying to compare this to natural gas or even hydrogen, that transport of those gases always leave a risk. And then, building the infrastructure also causes additional problems. So it's much easier to be able to move in an SMR into an area and then have just electrical distribution much closer. Just some things to think about. So now we will look at some potential SMR use cases, specifically in Norway. So there's a need for stable electricity, and I think most of us already realize now that there are things that happen in the world that we don't have a lot of control over, and it can affect how our electricity is produced and the stability of that And then we also have set a very ambitious goal to reduce emissions by 55% by 2030, and then to zero emissions by 2050. That's a very ambitious and tough goal. So how are we going to do that? Plus, we know that a lot of those ways to reduce those emissions also come with a electricity requirement. You need electricity to power electrical vehicles. According to the DNV's Energy Transition Norway report that was created in 2021, Norway will likely only achieve 24% reduction by 2030 and a 79% reduction by 2050. So these are just, and then as you know, those are goals and we try to get there, but we need to be realistic with this as well. And we also increase electricity. The demand is increasing as we increase the use of electrical vehicles and other forms of electrical transportation. So why should we consider nuclear for Norway? Hydropower is still the primary electricity source in Norway today. And as things change, it will continue to be a very large production point in Norway. But we also use oil and gas. So Norway has invested a lot in hydrogen and battery technology in recent years, but those are moving forward, and that's a good thing. But we still use fossil fuels, even though we're adding renewables and batteries and other gaseous fuels. So how do we get to the point where we are, able to support that? Sorry about that. So moving forward from there, potential use cases in Norway. So we look at maritime also. This is another thing that Norway is a very big maritime leader in the world. And so as Norway goes, the world seems to go. So we're looking at this. There's already a couple of projects. NTNU new pro ship project is underway, and then also the Ulstein Thor concept were discussed in some nuclear news and other industry articles. Nuclear is a near zero emission alternative to marine oil gas. Zero emissions also other alternatives such as hydrogen and ammonia. Unfortunately, for most, that takes up a lot of space. And then if you're talking about the fishing industry, you're also talking about that it basically takes up their cargo space. So we must be realistic about how we can move forward with this. And both of these projects are looking at the how to use nuclear on a vessel, whether it be a shipping vessel or a fishing vessel. So we're moving forward with that, and it's very interesting times. There's a lot of discussion with that today both in Norway and the world. Remote locations. This is one of the things where SMRs and microreactors can really have a big impact and help reduce the use of fossil fuels, because they have such a smaller footprint and they can be located in a little bit nearer to the sites or to the areas that need them. It would provide much more stable electricity, and then it allows those areas to maintain their electrical usage without having to rely on fossil fuels, especially in the mountainous areas. Wouldn't be a barrier any longer, because you could easily build an SMR in those areas or a microreactor, because not all of those towns require a 300 megawatts electricity production. It could be as simple as 10 to 20 megawatts electric. And then they can provide the energy security to those remote areas and islands that have a hard time connecting to the grid. As we said, also district heating can be produced with a microreactor like the eVinci. You get 13 megawatts or 8 additional megawatts of district heating in those areas. And then some other local electrification areas. And this was one of the things that we didn't initially think about, but now that it was brought up and discussed, it actually makes a lot of sense. You have things like the airport that can be completely off the grid self-sufficient for electricity demands for all components that they need. And then still have that connection that if when you need to take the reactor down for maintenance or anything like that, then you can put it back on the grid at low use times. But otherwise, it's basically self-sufficient. Same thing that this we talked about in industrial areas. As industrials grow, they're going to need more and more electricity. Well, where's that electricity coming from? So you have to think about, can we put a microreactor or a small modular reactor nearby an industrial area to supply that grid for that area and provide good, reliable energy at all times so production can go on. And then especially when you get into when we're talking about companies wanting to go electric with all of their vehicles, trying to charge a lot of delivery vehicles at the end of the day puts an extreme stress on the grid. So if they had a microreactor or a small modular reactor nearby where they could easily charge theirs, and then under those times that they're not using all the power, they can either reduce the power or send it out to the grid, support the grid in that way as well. And then as we look at the integration of everything, we want to use those renewable energies, the wind, the solar, the hydrogen, the batteries. Those things are in one part of that. And then we need to include nuclear as part of that as well to help support a stable electric grid and reduction of fossil fuels. And this allows us by helping us produce hydrogen, supporting industry, providing clean water, and then providing other industrial processes that help us improve our lives as a whole. So some of the conclusions out of this are that there is an increasing need for Norway to produce a secure and stable electricity for national consumption. So just like I talked about, as we move away from fossil fuels, as we go to a more electrical driven economy and society, the need for electricity is going to go up. It's not going to go down. So we need to look at, how do we provide that electricity without increasing the need for fossil fuels. And then SMRs offers that flexibility and integration, that they're small, including microreactors could easily be placed in certain areas that would support the increase in electrification. And then there's, as we saw, there's some attractive use cases in the immediate future for SMRs in Norway. I'd like to thank you for this. Sorry for some of my little mix-ups and bloopers, but I appreciate your time. Cesarda?
Thank you so much, Rob. So with that, I think it's time to have a small break. We will continue quarter past, so it's 8 minutes. And in the meantime, there's also provided some links to articles, for instance, by Jonas and others in the chat. So feel free to have a look at those as well. And with that, I would like to introduce our first speaker after the break, which is Jan Embleksvåg. So Jan has served in various actually senior management positions in the industry, including SVP of ship design systems at Rolls-Royce Marine and general manager at Midtsund Bruk, designing and manufacturing advanced pressure vessels. He is currently a professor at Norwegian University of Science and Technology, NTNU, board member, consultant, author, and speaker. His areas of expertise include operations management, product and process development, life cycle analysis, and renewable energy, including nuclear energy. He typically takes a techno-economic environmental approach to develop solutions to challenges at hand, and has written several books internally available and dozens of internationally published journal papers. He holds a PhD from 1999 and a Master of Science from Georgia Institute of Technology from 95, and actually one from NTNU on 94 as well. So Jan, the screen is yours.
Thank you for the nice introduction, and thank you for having me here. Let's see, let me share my screen. Is it visible now? Yes, excellent. All right, so I hold a lot of talks these days, and if we look at the key risks people think of, we can, put them into 3 big bags. Waste. We heard that waste issue is huge and long lasting. Cost. The nuclear technology is very expensive. Time. We do not have time. Nuclear power plants take too long time to build, and fourth generation is too far ahead. That's what we hear. All right. Well, first, waste. What are the realities? And here I got a nice picture from Zwilag in Switzerland, to use our country of similar size. And the key issue is that 99.5% of the radiation is found in only 10.2% of the material. And it's this kind of material that you find here. And after 40 years, only 1 per mil of the radiation is left. By year end 2018, there was about 2,400 cubic meter of material, and that's what you see here in Switzerland. And from this, they had generated almost 2,700 terawatt hours of electricity since the late 70s, I think. Now, with generation 4 nuclear power, the same amount of waste would have given up to 100,000 terawatt hours. Or, yeah, and of course, in terms of waste, which is very important, 70% of that material must be stored for 300 years and the rest for only 10 years. Unlike today, where we're talking about thousands of years. And of course, if we wanted to produce 2,700 terawatt hour, then we would, in the best case, end up only with this amount of waste, using the most efficient fourth generation technology that is now under development. So in terms of waste, I would say there's perhaps no industry with less waste problem than the nuclear when we look at the total picture. Today, we generate more than 50 million tons of e-waste globally, just for reference. The burden of nature is also minimal, and we see that here is solar PV, this is tons of material per terawatt hour produced. We see hydro, wind, geothermal, and nuclear by far the best, and radioactive material doesn't even show up. It's that little. And then, of course, we have this situation. The quote is from Deng Xiaoping. He said in the 80s, I think, that the Middle East has oil, China has Re. And we are now seeing the consequences of playing ourselves into the hand of the Russian bear with using gas and renewables. And I question the wisdom of playing ourselves into the hands of the Chinese dragon, where we already are. All right, and here are 2 books, very, very good books, highly recommendable to read about this. Okay, cost is another big thing, and of course people always use Hinkley Point C in the UK as a reference point for this. First of all, it's very, very untypical, but just for the sake of reference, it's still a quite interesting case. And the fact is that, of course, it's the financing, as we see, which is really expensive. If I look at the construction cost, it's only 17 euro per kilowatt hour, to use Norwegian terms. And fuel, 7, OPEX, 11, and waste and decommissioning, only 5. Now, what makes this so expensive is that the deal that was struck with the government and our French-Chinese consortium was that they also had to provide the financing. And they were smart enough to negotiate a 9% return on profit. And with this kind of production over 35 years, you actually end up with 100 billion euros in inflation-adjusted profit calculated into this strike price. And it's a new reactor design, of course. We've seen that in Flamanville, and also the Finnish one have had some issues, but this is well known in all industries. In marine industries, where I come from, we have built many things, and it's very rarely that the first one is out without any problems. But also, if we look at the grander picture, calculate the LCOE on a number of discounting rates and number of countries and so on. And these are quite revealing. And the first thing we need to know is that after the facility has been discounted, it's actually very cheap. The total nuclear US fleet today operates at about 30 euro per kilowatt hour in terms of price. If we build a new large hydroelectric power plant here in Norway, we would actually end up on this level, according to NVE, the Norwegian regulator. But look at South Korea. is already there on the nuclear, on the LCOE. And what the South Koreans have realized that the others haven't, apparently, is that you make one design and you just build the same thing over and over and over again. And because of that, they haven't had all these rounds of relicensing, changes, engineering, delays, everything. They build these reactors at, between 5, 6, 7, 8 years, depending on the local issues. It's also very competitive. So here I just put up a simple calculation between the South Korean APR 1400 and offshore wind, which is now proposed in the North Sea. And this is, it's 1500 megawatt capacity, 8-year construction time. I took the best numbers in the industry, which mean you end up at 45 billion NOK for this. You would produce 7 terawatt hours per year for 25 years. You need balancing of this, which is of course never included. And the LCOE target is $60 per megawatt hour. Now the APR has 1400 megawatt, 5-year construction time, 30 mega NOK per megawatt, which give you about 42 billion NOK construction cost. 11 terawatt hour per year for 60 years. You don't need balancing, and the LCOE is about 30. And if you don't believe me, well, here are the numbers from Poland. This is the numbers from the latest bidding round. And as we can see, the APR 1400 is about 25 million NOK per million per megawatt. And including financing, you end up at roughly 30, which is what I used. So it's highly competitive. Time is something we often hear, and here's a very nice study from Science, which is a highly reputed journal. And here we look at 10 years of rapid investment. And here we see the production per capita. And as we see, nuclear is by far the most effective. And take a look at Sweden. They built 12 reactors over 15 years. Of course, it's a smaller country, but look at France. It's a large country. Did very rapid escalation. So I would say when we look at risk, we also have to look at the other risks. And the real risk at hand here is a complete failure of the whole transition. And these are the primary energy numbers used the substitution method, which is the one the IPCC uses. And what have we achieved? Well, over 20 years, the renewable energy policy have achieved 4% improvement, and you can hardly see the solar and wind power up here to the right. This has so far cost $2.7 trillion. And another interesting fact is that with 99.6% correlation with population, and we know that every year the population on the planet increases by between 70 to 80 million per year. And we see this development, we really need to think fresh. We need new ideas. And I think what we talk about in this seminar is, of course, this new idea. Basically, we need to pick up where we left in the 70s, but of course with improved technologies. And it's all really about energy density. Here's a very nice chart that DNV has made, and you can see diesel is kind of in the cross in the middle. So the red area means it's less effective in terms of weight and volume. And here we see a number of solutions discussed today. Let's take a look at LNG, for example. It's a quite good fuel, but including the equipment, we end up in the red zone, so to speak. Methanol is already there, ammonia's there. Look at batteries, almost close to zero almost. If we look at hydrogen, we are, let's see what happened now. There we go, yeah. If we look at hydrogen, it's far out to the right, which is good in terms of gravimetric density. But when we include all the equipment, we almost end up in Origo. So now the key is that if this arrow is 1 meter on this graph, then uranium would be 32,000 meters out, and thorium would be 38,000 meters out. That means if we place those two into this graph, this entire graph would be more or less just a point like the batteries here. And energy density is something we really need to get back to into this transition, and also basic thermodynamic understanding. All right, so let's have a look at the deep sea challenge, which is really a quite revealing case. Here we have SMR, huge container vessel, and if we look at the 580 largest such container vessels, ignoring bulkers, tankers, cruisers, and all the other ones, but let's just look at the 580 largest. Well, data from Shanghai to Amsterdam, then we know that one of these guys needs about 3,350 megawatt hours per day. With heavy fuel oil, that gives us 350 ton consumption per day, or roughly 3,900 tons each way. With green ammonia, we have half the burn value, which means we need twice as much fuel. And with 12 megawatt hours per ton in terms of electrolysis, and we assume 80% utilization of the ships, we end up with soon, just hold on, just for reference, 1 terawatt hour per year in terms of thermal power, but green ammonia, we need actually 2.2 terawatt hour per year electric power for each ship. Then, of course, comes all the losses, balancing, etc., etc. That means the entire Norwegian wind production in 2020 could produce almost enough to 5 such ships. If we look at entire energy production in Europe, electricity production in Europe, these 580 largest container vessels would require almost somewhere between a quarter and half of Europe's total energy production. And if you look at all the heavy fuel oil consumption in the world, in the marine industry, about 300 million tons, that would require twice the entire European electricity production. Obviously, completely unrealistic, unsustainable by far. So we did some calculations, took a 2-stroke heavy fuel oil engine, Wärtsilä engine. This is operating on a tanker between Singapore and the Persian Gulf. I dug out some number from the Fuji reactor work in Japan, because they have published quite a lot of details. Of course, there's a lot of uncertainty, but anyway, by the way, for reference, as we know, the molten salt reactor has this freeze plug, cut the power, and it stops. So it's extremely safe in that respect. Or actually in all respects. Now, if we then look at 30-year lifespan, assuming 7% discounting factor, the molten salt reactor would outcompete the heavy fuel oil head on head by almost 400-500 million kroner. Now we start talking. Now we can use the power of the economic system. This means a better solution will outperform a worse solution. Keep in mind, we did not venture out of the Stone Age because we ran out of stones. Neither did we stop burning fire because we ran out of wood. You know, we used coal, we used all the other ones, the fossil that we today use, because they are more efficient. This is the next step. That's the point. So in terms of shipping, then we have 2 basic possibilities: direct nuclear propulsion, with a lot of interesting possibilities, faster ships, lower cost, no emissions, and of course with a 4th generation reactor, preferably walkaway safe or at least passive safety. Of course, challenges that we will highlight in a project that is soon coming. We can also look at synthetic fuel. We can use nuclear reactors on land, manufacture zero emission fuel. The good thing is that we wouldn't have to change much of today's install base. Lots of potential challenges in terms of cost, you know, volume, safety might also be because of hydrogen is a quite, what should I say, quarrelsome atom, and a little bit static electricity and so on can give a very, very large explosion. It's being said that 1 kilogram hydrogen is about 1 kilogram TNT, for reference in terms of explosive power. So this brings me to the NewPro Ship 1 project that was mentioned earlier here. We have obtained 10 million public funding and of course some in kind from the companies. And this vessel consumes about 40,000 tons heavy fuel oil per year, which gives 120,000 tons CO2, 720 tons of SO2, and a host of minor emissions, including cadmium and that kind of stuff. So we have said that we need passive or walkaway safe. They have to be a certain development stage, typical size 50 to 150 megawatt. And with the initial project that we have concluded, we ended up with 3 interesting candidates. One is the SMR reactor from Sweden, which is originally a Russian, the Brest reactor, but they have done improvements, so we call it SMR. Then we look at helium-cooled gas reactor. And of course, some version of the molten salt reactors. We haven't quite decided yet. There are quite many different versions to look at, all with some pros and cons, but all these are interesting cases that will be looked at. Now, but this is not the only thing. Actually, this is only work package 1. Perhaps the most important work packages are number 2 and 3, because they will look at the entire, what you say, ecosystem around nuclear shipping, safety, regulations, technical implications for the ship, operational safety, the requirements for the crew and maintenance and the whole and everything, including, you know, port handling and, you know, docking, yeah, everything. And of course, we have to look at the performance in the end. So starts in January, delayed from August because of the situation in the Research Council. But here are the companies and organizations involved in this first project. And we are also in the process of establishing number 2, which will be a genuine development project. As you can see, this is a concept and feasibility study. So main objective is to sort out and to identify key requirements that we have to fulfill really in the next major project. Yes, and in the end, I think when we talk about risks and we talk about nuclear, it's easy to talk about all the bad things that can happen, but we also have to start considering in earnest all the good things not happening. And I think when we look at the total equation, nuclear is by far the best option we have in this energy transition. Yes, and that's it, folks.
Thank you so much, Jan. The next presenter is Simon Johansson. So he manages the European affairs actually at the Norwegian Ship Owners Association and has previously headed up their office in Brussels. Since the last 2 years, he has had a particular focus on coordinating input from shipping into the EU's Fit for 55 package. He has a background from foreign affairs and trade and has previously also worked for the Norway's mission to Europe and also the North Norway's Brussels office and the US Embassy in Oslo. And he holds a master's degree in political economy from BI, Norwegian Business School. So Simon, the screen is yours.
Thanks very much. I'll just pull up my presentation here. And thanks very much for the invitation to speak about something not nuclear. I'll tell you that nuclear is certainly on the agenda among our membership. We discussed it this Tuesday among our members in another seminar here. And Jan, thanks to your presentation, I see one of our members, Knudsen, is in your project group. So it's certainly something that's on our agenda. I've been invited to say something about how we have given input into sort of the ongoing environmental regulations that are coming at the EU level for shipping. As you know, the backdrop of all of this is that ideally we may have wanted some global regulations, environmental regulations, but in the past 2 to 3 years, we have seen a real push at the EU level. And we're really, in these couple of months going into Christmas and into the next year, we may actually see sort of the finalization of a 2-year process and have a whole wealth of new environmental regulations kicking in for shipping. So what I thought I'd do is just give you a bit of a flavor of how we've been covering this from our membership. We represent the foreign-going fleet of Norway, so about 130 companies, 1,400 vessels, and a fairly diverse fleet of deep sea, short sea, and also, of course, a specialty in offshore. I'll start with a little bit of a process, and I hope you can see the slides here. I'm sure you'll be familiar with the EU's Green Deal and the Fit for 55 package work that's been going on for 2 years now. I've been covering this from Brussels since 2019, and I think we were surprised at that time when after the election in 2019, with the new mandate, the new commission that came in, just how large the ambitions were and how quickly they wanted to move. And even despite COVID and some other global developments, we've really seen this work progress very fast, and they're really on schedule to implement this. So the second large step was, of course, about a year after the presentation of the Green Deal, was to increase the 2030 ambitions, and then about a 10-month consultation process to see what exactly will this need in terms of resources and sort of sharing the emission cuts, and then what is the actual proposal for a lot of different sectors. So this all came out last summer in July, a massive package, the largest package, legal package ever presented at the EU level. And we, as many other sectors, have had a lot of resources dedicated to just analyzing exactly what our interest and exposure is. So this is maybe the map that we've identified for ourselves in shipping. There are 12 or 14 different proposals, depending on how you count it. And for us, the main proposals for shipping are, of course, the revision of the ETS, the emissions trading system at the EU level. So this is, I think it's important to stress that this is a revision of the complete emissions trading system. So we're just a sector that's being taken into the mix, but we're only one of many sectors into that proposal. And then there's also a dedicated proposal on alternative fuels use in maritime. And then these two main proposals, of course, have to be coordinated very closely with alternative energy directives, with energy taxation, with this carbon border adjustment mechanism, and a bunch of the others. So this is all very interconnected. For us, as I was saying, this is really a massive revision of the emissions trading system. So while we've been keeping an eye on the shipping interests here, this is also being negotiated for a lot of other sectors, and the ambitions are really being turned up. So you're cutting the overall amount of emissions allowed. You want to increase it from a percentage in the 40s up to 60s by 2030, and also include not only shipping, but also land transport and other sectors as well. So that's some of the substance there. On the fuel side, there's been proposed sort of a stepwise phase-in of requirements on the CO2 content or the emissions content in your or alternative the percentage of alternative energy in your fuel mix year by year, going up to around 75%. This is still being negotiated, but those are sort of the two main pillars that we're following from shipping side. Just to give you a little bit of a sense of how we've followed it from shipping, we're organized in a European umbrella organization within European shipping. So since this is a regional initiative, we've really been sort of spearheading that effort at the European level. We're the second largest member of this umbrella organization from the Norwegian side, and we probably have the most diverse fleet as well. So we have to keep an extra eye out for specialty vessels, offshore. Yeah, we have more interest than some of the others here. And in terms of our input into the process, we really have been in very close partnership with the Commission as they were developing the initial proposal. This is, shipping is not an easy sector to regulate with many moving parts and foreign ownership and a lot of extra factors. So we've really been a partner in the consultations and have proposed a lot of the models that eventually were taken into the proposal that came last summer. And then we've also been very keen to follow up at the Norwegian level as this sort of churns through the machine in Norway as well. What Norway will pick up from this and also sort of their input into the process. And then I'll get back to a little bit of the process that's going now. In terms of what this will mean, these are some of the variables that we've been considering as we input into the process. I mean, initially, one of the big reasons probably why shipping hasn't been included is where to draw sort of the geographic scope of something like this. So should Europe start only with intra-EU shipping? Should you try to include some other emissions, or should you go for all emissions, for all ships sort of coming in and out of EU? And the proposal currently has landed sort of in the middle. There will be a full quota for emissions within Europe, so from port to port within Europe, and then 50% of the emissions sailing in and out of Europe. So that was a first important point. The second point was which ships will be included. So there's already a monitoring and reporting system for all ships over 5,000 BT GT. The proposal currently has been reopened a little bit by the Parliament and the Council. They want to include also smaller ships and remove the exemption for offshore. If that happens, then of course the Norwegian fleet would be included to a much larger degree, and that's something we're following closely. We're of course interested in the cost of all this, of the phase-in. I think in terms of our membership, we're most interested just to getting some clarity in terms of what the regulations will be, who will be included, and when this will start. And that's been our approach really from the start. We decided there were two ways we could look at this. We could either try to fight it and ask for global regulations, or we could lean into it and try to have a hand on the wheel. And from the Norwegian side, we already are very much aligned with the climate or the ambitions at the European level. And we only see this as a positive to lean into this and just get a system that works well. In terms of the process going forward, we are now in the final phase, actually. So after the package was presented last summer, it was sort of pushed over to the European Parliament and to the member states to deliberate and take their positions. So a lot of the issues that were concluded by the Commission initially were then reopened by the different parties and the member states. And they have proposed sort of independently adjustments to the package that came last year. So we're now into the final phase. The ETS package is being negotiated as we speak. It's going faster than expected. So I was in Brussels last week, and now the latest ambition is actually to conclude it before New Year's, sometime in December. We'll see if they manage that, but that's the plan. And on Fuel EU, the Maritime, they just concluded the Parliament's position, so now they can get into a similar process between the three institutions, probably concluding sometime this winter. So those will be the main two pillars. We're very keen to see this part of the work concluded. And for us, one of the main sort of follow-up points moving on from all this is to see a lot or some of the revenue returned to industry. This will be a fairly large pot of money coming in from shipping. We have estimated just most likely the Norwegian contribution will be somewhere between 200 and 300 million euros a year when it's fully phased in. So we're developing some argumentation. I want to see this money not just sort of going into state budgets and other places, but actually going towards greening initiatives in the maritime sector. So maybe finally, I touched on some of this, but as we see this process concluding at the EU level for this first phase, we are working closely with authorities here in Norway to actually map out exactly how this will work in practice. You know, there are a lot of moving objects. We will essentially, I think at this time of Norwegian companies included in the ETS, it's about 130, 140, and most likely it will be up to 100 new shipping companies. So we will almost double the number of companies, Norwegian companies in the ETS. For the first time, a lot of these installations, previously it's been a lot of factories, now it will be ships. So there are a lot of moving parts and a lot of moving ownership. So we need to nail that down. At the EU level, we are preparing actually for the most likely when they conclude this package, they will start work on 2040 goals. So they will try to flesh out the journey towards 2050. So we're essentially just getting back into the same kind of work, but working towards 2040, not just 2030 and 50. And then in the backdrop of all this for shipping, it's of course very relevant what effect nailing down this package at the EU level will have on negotiations at the IMO level. And this has been going in the background since the climate strategy of the IMO, or the ambitions were taken in 2018. There will be a major revision, most likely next summer, of the overall ambitions at the IMO level for the shipping sector. And we've also started discussions on sort of the use of market mechanisms of a levy, of maybe a quota system. There are different models on the table, but we're very curious and keen to see some progress on that at the IMO level. So that was a bit of a flavor on what we see coming and some of the effects on shipping, but happy to take a few questions.
Thank you so much, Simon. Okay, thank you. No further hands for the moment. And we will keep Andre on the spotlight. He is our next presenter. He graduated back in 2002 with both nuclear engineering and economics University in Romania. He also holds a master in nuclear safety and radiological protection. You have experience from working at, was it Mochovke Units 3 and 4 project in Slovakia, and then sort of moved on to working at nuclear electricity in Romania, and now you're in Nuclear Europe, has been there since 2015, holding now a position of policy director. So the screen is yours, Andre.
Thank you very much. I already intervened several times, but a very interesting event, and thank you very much for the invitation. Yeah, I have to be honest. I adjusted a little bit my presentation based on what was presented before. So it was said a lot about SMRs. And I will say something about what is going on at EU level regarding nuclear and the impacts on nuclear on different issues. Very briefly, some words about my organization is the Trade Association of the Nuclear Industry. We are an association of associations, but we have also some corporate members, you can see. Unfortunately, we don't have anyone from Norway, but we have some non-EU members like Ukraine, Switzerland, and recently UK. Yeah, we are. This is a standard slide showing what is the contribution to the EU economy. One point about the 25% on the electricity production. This unfortunately will decrease most probably this year's because we are talking about some shutdowns both in Belgium and Germany. So we will see. But we are there. So 1/4, more or less, it's produced by nuclear, even though the policies are not mentioning so much this source. Some thoughts about the future of nuclear in the EU. And yes, these are some scenarios that were published recently. You can see that nuclear will still exist, depending very much on the capacity, installed capacity, but also on the final production. Are you still? Yes, it was a problem with my presentation.
You just reshare it. I think we'll be back.
Yes.
Thank you.
Yes, it's back. But in a nutshell, we had a report that we published in 2021, and it's clear that there is a large missing capacity of nuclear between the EU scenarios and what we are seeing. And part of this missing capacity, of course, will be also SMRs. So we can see that there are more and more discussions about SMRs at EU level. This is a very general slide, and it's somehow in line with what Simon presented. Is what is the sector focusing on EU energy policy. So we are looking at a very broad range of policies. We are trying to understand how those policies can impact the nuclear sector, and of course we are trying to intervene. We had so the policies are shaped at EU level based mostly on the national energy and climate plans, the energy policies, and we did a screening of these national energy and climate plans, and you can see that there are a lot of member states, some of them not operating nuclear reactors, which are still considering and having mentioned in the documents the nuclear, depending different areas. And the balance of powers in because we are talking about politics, and it was mentioned also the council. In the council, so we have 27 member states, and in the past we had 28, but with the departure of UK, with the Brexit, we lost somehow the center of the weight, because of course UK was very supportive for nuclear. You can see, well, there are not all the member states mentioned, but you can see that we have quite strong nuclear opponents, so Austria, Germany, and Luxembourg, the trio. Italy is still like a nuclear opponent, but we have to see, because things are changing. There were some mentions exactly about SMRs in Italy. Then we have the pro-nuclear member states, which are clearly mentioned, and we can see that Central and Eastern European countries, France and Finland, but also recently we have good news from Sweden, and there are some countries which are still assessing their nuclear future. Spain, they're operating a fleet of reactors, but They didn't decide yet on the long-term operation or other new build. Poland, some recent announcements, is still is still mentioned as considering their nuclear future, but I think that we can change it to green. And Estonia, for example, it's considering to build an SMR. Also, Belgium is still assessing the future. Some developments of the policies that I was mentioning before. So the European Green Deal, very important initiative of this Commission. So European Green Deal and Fit for 55. 55 is coming from the decarbonization targets for 2030. And then we have net zero emissions by 2050. So this is the decarbonization target. But we have also some targets, other targets for renewable and energy efficiency. We always consider that those targets are should be only, let's say, to help, not to have clear targets for other technologies or initiatives. But yes, the policymakers are still considering. So we had in the previous packages 40% for renewables and from 36 to 39% for energy efficiency. And this is the decarbonization path. And I'm going back to what Robert said about 2030. You can see 2030 is around the corner, I would say. But very interesting, the EU is aiming at decarbonizing the power sector, one of the first sectors to reach net zero, and it's in 2040. So the time is very short, I would say, and the ambitions are very, very high. And I was mentioning our report from 2021. It's a very interesting outcome. You can see that for the for 2030, 2032, no, 2023, 2027, sorry, on medium term, it's very interesting that in the low nuclear scenario, the emissions are actually, the emissions of the power sector are increasing. So if we are not choosing to continue the operation of the existing nuclear fleet. After that, things are getting on track, but this is something of very high concern. Then we had the REPowerEU, the newest initiative, and I was again about targets. Those were the targets presented before. Now we are going even more. So the targets are more ambitious, so more renewables and the energy efficiency as well. We don't have more information how those targets will be achieved, but it's a very interesting chart about the gross inland consumption by fuel. And you can see in 2030, Fit for 55 was forecasting those figures. And then in the new REPowerEU, we have new figures. Very interesting that actually nuclear with dark blue here, it's increasing, but we don't understand exactly where this increase is coming from. I hope that it's coming from some SMRs we're taking into consideration. One very, very important point and a very important piece of legislation that we were following for the last 2.5 years, I think. And it's very important because we are coming, this can have a very big impact on the financing of nuclear, and we saw that the financing is very expensive. So it's the sustainable finance, and we had finally adopted on 15th of July the complementary delegated act, which are considering the nuclear as well gas, with of course some disclaimers, are considering as green. Those disclaimers are regarding the technologies, and they are considering both technologies, gas and nuclear, as transitional. But for nuclear, there are some, for generation 4, there are not so, there is not deadline, I would say. So with generation 4 and the advantages brought by the generation 4 reactors, we can think about way longer perspective for nuclear. Legally challenged. I will not get into details, but this was a big, I would say, success that we managed to achieve recently. Then another very important topic and very trendy topic at EU level, it's about the hydrogen strategy. We had a position paper where we are mentioning that nuclear can also produce hydrogen, help producing hydrogen through electrolysis, but later on also with the high temperature reactor directly using the high temperature heat. One very important matter would be that the ambitions are very, very high on the usage of the hydrogen. I'm not sure if all the industries are ready to incorporate such a big consumption of hydrogen. I'm saying that, and I think that it's important to be highlighted, because sometimes the policies are made starting from the targets, and after that trying to get to the results. One thing that we are keep saying, so beside the hydrogen, we are talking about the production of heat of the nuclear reactors, large, small, micro, and also advanced reactors. Heat for district heating and industry processes. And of course, I think that from this slide, now I realize that is missing the transport. So I have to think about it. And another thing that we have to keep in mind, that nuclear is not just power. It's having different other applications, and definitely it's a strong point that we have to make. Some figures about comparison of nuclear with other low carbon technologies. So for 1 terawatt hour produce electricity, each technology generates, and you can see what are the numbers on billion euros on the EU GDP per year. So you can see that nuclear is very high. Also, the comparison on jobs, you can find more in our report published on 2019. And also very, very interesting about the impact of nuclear on the share on the EU GDP. Is very important to mention that, and the figures are so high, or the importance of nuclear is so high, because it's I would say a very localized sector or technology. So most of the components are produced here in Europe. So that's why the impact is so high. So we are not importing, and yes, consequently not having such a high impact. Some thoughts about security of energy supply and energy prices, because we are talking these days about these issues. Very high energy concentration, and there is no problem with uranium shortages. This is another risk that the anti-nuclear organizations are seeing. And also, when we are talking about uranium supplies, we see that, for example, 20% are coming from Russia in 2021, but the market is flexible enough to provide enough uranium resources from elsewhere. And on energy prices, this is I think it's an interesting figure regarding the impact of the price of uranium on the overall production costs. So you can see that the fuel overall, it's only 34% out of the nuclear operating cost, and out of it, uranium is 41%. So all in all, we have around 15% the impact of the uranium in the overall operating cost. And if the uranium costs are increasing with 10%, the impacts on the operating costs are minimum. And some words about small modular reactors. Here I removed some slides because they were very well presented before us. We had a position paper very recently published. You can see what it's more a general position paper. What is the position of the nuclear industry towards the SMRs? We are using for the discussion with the policymakers and to raise awareness about this technology. Not going into the definition, it was said before, but we can see that we have really a lot of designs proposed in different stages, and maybe the most important is the newest timeline proposed by the IAEA. It was a document recently published. And we can see that 2030 is coming, it's around the corner, and we see that a lot of them might be deployed by then. It's interesting to see how this timeline is developing over the years. So you can see the comparison between two editions of the same document. The things are speeding up, and it's a very good news, I would say. And I wanted just to highlight some of the designs that are foreseen for some organizations in Europe to be deployed. So we have PVRX, Rolls-Royce, Newart, and NewScale. I cannot pronounce the new acronym. It's a little bit complicated. And there is another one from Czech Republic, Teplator. I saw it. It's for 2029, and hopefully they will succeed to keep the timeline. So all in all, this is the presentation from my side. These are the differences, so single unit or multiple units, and some pictures about the reactors to be deployed in Europe. And also in our report 2020, November 2021, we were taking into account some figures about SMRs and Generation 4, but I can tell you that it's more SMRs, and I'm pretty sure that these figures are much higher these days. So we are trying to get new figures and to publish something new on this topic. Thank you very much for your attention, and I'm open for questions.
Thank you so much, Andrei. Then we will move on to our next presenter. Let's see, that's Jonny Hesthammer. He's a geologist and geophysicist with background from Statoil, and also former professor at the University of Bergen. He became the chairman recently and acting CEO of the nuclear power startup Norsk Kjernekraft AS, a company that aims at building nuclear power plants in Norway. And he has, together with Dr. Synnøve Rose, written numerous newspaper articles on the climate change, energy, and the nuclear power. So the screen is yours, Jonny. We look forward to the presentation.
Thank you very much. It's such a great pleasure to be able to speak to you all as the CEO of this nuclear power startup in Norway. So what I was thinking I would do was to say a few words about this company, and then go on to say why we think nuclear power is a good idea for Norway. So just to start off with a team. So with me on the management team, I have then Sunniva Rose, who is the CEO, the CCO, the Chief Communication Officer in the company. We have Steffen Sæle, who is the Chief Engineer, and we have Håvard Christiansen, who's the Chief Operating Officer. And I must say, I'm very, very pleased to have been able to gather together such a fantastic team of competent people. On the board with me, I have Christian Tveit, who is the CFO of another company. I have Susanne Sperrevik, who is a geologist, and Åse Strømme, who is a reservoir engineer. We have worked together for many, many years. We know each other really well, and we think that is a great advantage when we are moving forward. And then, of course, if you want to build a nuclear power company in Norway, you need some good investors. So what we have here is Trond Mohn, who is a renowned industrial builder from the west coast of Norway, building up Framo Engineering, and he is also one of the richer men in Norway. And with him, we have Lars Mollestad, who has been working with the oil service industry for many, many years. We have also partnered up with a couple of entities. Very pleased to have partnered up with IFE, and of course I don't need to say anything about them because you already know a lot about IFE. So I will draw the attention to Apollo Plus, which is a Swiss-based consultancy company with very extensive experience within regulations and security aspects. They have been engaged and been consulting a number of nuclear organizations worldwide. So that's a very good startup. Building a nuclear power company in Norway it's going to take time. We know this is we're talking a decade ahead in time at least before we can get anything in place. So what we are in need of doing is to have a shorter term perspective on what we can do over the next few years. So for the period until the end of 2025, we are going to focus on identifying areas that are suitable for small modular reactors. Then we're going to focus on preparing the basis for a license application. And a very important thing in Norway, since we don't have nuclear power from beforehand, is the communication to the politicians and to the public. We see that it's like, I guess, with Iceland, where you don't have snakes. That's a country where they're most afraid of snakes. And I think in Norway is a little bit similar in that respect when it comes to nuclear power. And in addition to that, we are focusing on securing strategic and industrial partnerships. So that is a short-term perspective on this. And if we succeed, I think we can see small modular reactors in Norway in the 1930s. Going on a little bit, just to put things in a bigger context, why we think there is a change that will also happen in Norway by starting looking at it a bit globally. Here we see from the BP statistical review the change in energy consumption in the period from 1990 to 2020. And what we can see here is that there has been an increase in energy consumption of 60%. So even though new renewables are growing, the share of renewables in the total energy mix, and I'm talking both inside and outside the electricity grid, then we see that in 1990 that was 14%. Today it is 12%, which is telling us that renewables are still not yet even able to keep up the pace of the increase in energy consumption. And because of that, fossil fuels are increasing. And we see how nuclear with the orange color here, they are staying fairly stable. So when we move ahead from 2020 to 2050, it will be speculation. So what will actually happen? But it does make sense to say that nuclear power should have an important role in that perspective. So when you look at this totality of the energy sources, we know that all the energy sources have their advantages and disadvantages. So it's weighing the pros and cons against each other. And we have done a fairly intense and deep study using published articles in renowned journals to look at these parameters that are now becoming a part of the common taxonomy evaluations. So when you do life cycle analysis. But this is a study we did where we looked at emissions, mortality, land use, material use, cost, waste, and stability. And Sunniva and I are, in particular, we are presenting this through these articles in the newspapers where we try to illustrate the disadvantages and advantages of the different energy sources. And we can see we highlighted nuclear with the yellow circle here. You see it comes out pretty well in all these evaluations. I won't go in detail on that. There is no time for that. But if you put all of those together and you look at the totality, asking yourself, which energy source has the least negative imprint on climate, health, economy, nature, and the environment? Then I'm going to show you a graph where we have done exactly that. So when it comes to these parameters, mortality, emission, land use, and so on, it is subjective how important they are. Some people would think climate or emission of CO2 is by far the most important. Other people are concerned about nature. Other people are concerned about the air pollution, things like that. So you can go in on this website and then you can actually do your own weighting of these different parameters. I've just put some in here. 50% for mortality, emissions of CO2 is most important, 100%, land use is 75%, and so on. But however you weight these parameters, you end up finding that nuclear comes out with the lowest negative imprint on climate, health, economy, nature, and the environment. This is sort of the things we're trying to tell people in Norway and tell the politicians, that nuclear is not as bad as many have the perception of. And luckily, there has been some reports coming out lately. And I think for all of those who are in this nuclear environment talking about this, we need to really understand these two reports. The uppermost here is from the Joint Research Centre. It's a science panel of the EU. And they did a very extensive study that was published last year, where they in particularly looked at the issues of safety and handling of waste. And what they concluded is that modern nuclear power, like the ones that are being built in Europe today, in Finland, in Great Britain, that is the safest energy source we have. In fact, they say in the report that if all the existing nuclear power plants in the world were replaced by these modern EPR nuclear power plants, then you could expect from a significant accident, you could expect a casualty every 315 years. That means 3 casualties every 1,000 years. There's no other energy source that's even close. Somebody will fall off the roof mounting solar panels on the roof long before that time period has passed. And then when it comes to the waste handling, what they are saying is that it's perfectly safe to store radioactive waste a few hundred meters in the subsurface, like they do in Finland. So, and then they do an evaluation of it and refer to some of these Finnish studies where they say that if there were to be a leakage of this waste in the distant future, the radiation that the public living in the area would be subjected to would be actually far lower than the background radiation you are subjected to anyway. So what they're saying is that it's perfectly safe. I think this is very important. This report, extremely important. Of course, it was used by the European Commission in regarding the taxonomy evaluation. But then there was a new report that came out very recently, and this is from the United Nations Economic Commission for Europe. And what they were doing, they did a life cycle analysis of all the different energy sources, and again, part of the taxonomy evaluation. And what this report says, and this is, I think, for the Green parties, I think this should be extremely important as well. What they are saying is that nuclear power has the lowest negative impact on ecosystems, which is about climate, nature, and the environment, on the resource use, which is the minerals and metals, and also on human health, including cancer. So what these reports are saying, and people may disagree with the content of the reports, but then they need to substantiate that. What these reports are saying is that nuclear power is in fact the best choice for the climate, for the nature, for the environment, and for the human health. So with that in mind, then we are moving over and saying, well, should we have then nuclear power in Norway? We do hear, and we heard that also during the presentation today, that Norway is lucky we have hydropower. But although we have electrified a lot of our energy use, the majority of the energy we are using is still outside the electricity grid. 60% is outside. And it is being used for heating and transportation. So those 60%, that's fossil fuels. So even if Norway has gotten far within the electricity mix, then where it's all renewable, we still have a long way to go. We're far better off than many countries in Europe, but we still have a way to go. So when I hear people talking about we can fix it by energy efficiency, upgrading hydropower plants and putting solar power on the roofs, and then we don't need more energy, I think they are missing that point. The other thing, and we saw earlier today, Rob was bringing up the energy transition from this DNV report, where they're saying we expect to be 1 million more people in 2050. They are all going to use electricity, and then we plan for energy-intensive industry like battery factories, hydrogen plants, and then carbon capture and storage, such things. So what they are saying that if you do extensive energy efficiency and you do structural changes, then you can limit the increase to maybe then another 100 terawatt hour by 2050. That's an increase of 65% from today's level. The problem with that is that you're approaching 40% of the energy mix coming from weather dependent power sources. And now I'm saying hydropower is not weather dependent. We have seen that it actually can be. So what I'm saying then is that the majority of the production, of the new production, is going to come from wind power, 75%. And of course, we are then, in order to handle that, because we then get power when the wind is blowing, we actually need to have cables going down to the continent of Europe so that we can import and export as needed. What that means is that we are then relying on a Europe that is currently in an energy crisis and that has a much further way to go to reach a net zero target and do the electrification of their own countries. So I think there is a challenge for us there, and it was highlighted in a very recent report that came up from NVE and Statnett, where they're saying that we're moving towards a trend now in Norway where we don't have much adjustable production capacity. And if we have wind poor periods, it will lead to a high demand for other types of generation simultaneously in many countries. And because there will be weather situations that can affect large areas covering many countries, they're saying that there is an uncertainty as to how much production capacity will be available at any given time for imports. This is why I think it's like if you are then to do something about it, they also say that this will have very high investment cost. And I think this is a very serious issue that the politicians in Norway need to address. And there is one solution that can do something about it and help out the challenge that lies ahead. And that is implementing small modular reactors in Norway. And these, we have talked about them before, these small modular reactors that are mass produced in dedicated factories. Here we see an example in the background, which is from GE Hitachi, and we have a couple of other ones, Rolls-Royce, up in the right corner. We think that for Norway, it makes sense to start off with sort of generation 3+ reactors based on existing technology. That's going to be a quicker way to get those in place. In the long run, then we can move to generation 4 and molten salt reactors and so on. I like the idea. We have a lot of coastline suitable for small modular reactors, but we are very fond of our nature. So taking one of these that occupies the area of a football stadium rather than placing windmills covering an area of 100 square kilometers for a similar amount of power output. It makes a lot of sense. I worked in the oil industry for many years. I've led a few oil companies, and I can see that the cost of these things is similar to actually the cost of building out a small oil field. But when I look at the economics of it, I see that you have at least as high economic potential. And I think this is a fantastic thing. I think actually oil companies should be maybe one of those who should be financing this. We don't need, with this kind of modules, we don't need state subsidies. We can do this private. And this is what we are aiming on. And I also think for the municipalities in Norway where people are living, a lot of people are working in the oil and gas industry, and we know that's going to be phased out. And then I think it's very good to address the fact that nuclear power creates jobs. This is a study from the International Monetary Fund, where they say that nuclear power provides the highest paying jobs, 1/3 more than renewables. It provides 25% more employment than wind power and also local employees. And only nuclear power provides significant and sustained work beyond the construction phase. So I think those are important arguments in favor of nuclear in Norway. And finally, the last slide, we do see that the population opinion, the opinion in the population is changing. There was a recent Norstat study where 38% are now in favor of nuclear power in Norway to help solve the climate crisis, whereas 32% are against. That means in Norway, we have reached this fantastic achievement. There are no more people, there are more people in favor than are against. And very recently, we saw this, there was a climate survey that came from Kantar, where they looked at onshore wind and nuclear power. They've done these polls back to 2009. And we see in 2009, 9% were in favor of nuclear power. Now it's 41% this year. Whereas onshore wind was 70% or close to 70% in 2009. Now it's down to 43%. Seems like wind is now taking a bit of an elevator downstairs while we are taking the elevator going up. And I think that is excellent for a startup company called Norsk Kjernekraft AS. Thank you very much.
Thank you so much, Jonny. Very good. With that, I think I would like to thank everyone for participating in this webinar on small modular reactors. I would give a special thanks to all our speakers, also especially the external ones. I think we had some good dialogue, but the dialogue will not stop here. We will have to continue this in different forums. So with that, I thank you all for participating.